All right. So, like I said, we're opening up a brand new chapter, kind of taking another step. You see, we have not done a whole lot of calculus yet. Actually, we've done zero calculus, but we learned all about 3D. We learned about what it takes to be in this kind of world of Calc 3. We learned about vectors, but we haven't done a lot with them. So today we're going to learn about something called vector functions. What we're working with for this whole chapter, how we start to think about calculus, how we start to think about what does a derivative even mean in 3D? What is that idea? Because if a derivative is a slope of a curve at a point, we don't have slope anymore. We have vectors now. We have these things called vectors, and we're going to talk about vector functions. So here's the few things I want you to know about vector functions right off the bat. Number one, vector functions, and I'll show you why, but vector functions are, man, they're just an extension of parametric equations. They literally are a parametric equation. Do you remember anything about parametric equations, like at all?
Yes.
I remember they got a whole lot of t's in them, like all the little t's. Well, yeah, that's going to be in vector functions also. So they're an extension of that. They are a parametric equation. In fact, I'm going to show it to you right now. So with our parametric equations, we normally saw them like this. We had x and we had y, and they were defined independently, but they were defined with the same parameter. That idea of parametric equation says, here's a parameter, it's one variable that's used to define two other dependent variables, like x and y. So we have x is a function of t, and we think of it normally in terms of time. Even though it doesn't really relate exactly, we think of it time. And then we would have y as a different function of t. Okay, here's my question. What's the only independent variable that we actually have here? T. X and y, even though they're variables, they depend on what the value of t is. That's the way that parametric equations work. So, this t, let's talk more about it. This t was called a parameter, and it was on some interval that gave a common domain for both of these other functions. It means that we can pick whatever t we want as long as it works in both of these functions. So if we have denominators, they still can't be equal to 0. If we have square roots, we still can't plug in numbers that are negative inside of square roots. So they have this common domain as well. So this t is the parameter for some interval I on a common domain. If you want like the English translation of this, it says, hey, you know what? X and Y are now no longer independent variables. Either one, they're both dependent. They depend on t. This t is the only variable that you can plug stuff in on the board right now. So it's called the parameter, and it's going to work for a certain interval so that both of these functions are defined. That's what that common domain means. It means that we got this interval of t for which these t's both work in both of our functions right now. Show of hands feel okay with that. That's from parametric, but I wanted to kind of clue you in. So, okay, now how do we extend the picture? Well, how many dimensions do you have here? Two variables, two axes, two dimensions. If we want to extend this to 3D, we just got to simply add another variable. Instead of just x and y, now let's talk about x, y, and z. You know, we're going to keep x as f of t. That looks pretty good. And y as g of t. And then, well, what's the only other variable that we're missing?
Z.
Question?
I was just wondering what your symbol was. What the symbol for 3D is, what it means.
Oh, you know what? I'm going to use several different ones. We can do 3D just to mean 3D. But R3, like this, is real numbers as you draw this box letter R. So the real number system in 3 dimensions is what that means. So have I never talked about that before? Good thing I brought it up now.
Thank you.
You're welcome. For 3 space, for R3, for 3D, same stuff. On a 3-dimensional coordinate system, same stuff. We need another dimension. We need a Z. So let's see, A, B, C, D, E, F, G. Why not? Okay, real quick, how many independent variables do we have right here? How many independent variables?
1.
There's still only 1. How many dependent? 3. In fact, it's really weird, right? Because this is still parametric, but it says for every value of t, I'm giving you an x and a y and a z coordinate. I'm still giving you a point. So for every single value of t, I get a little point in 3D. You can see how we could move around every space in 3D according to this sort of a system. It's parametric. The variable is t. It's called a parameter. Our dependent variables are x, y, and z. We can get a point by plugging in a value of t. Head nod if you're okay with me on that stuff. All right. Now let's put it together. T is still our parameter, by the way. I'm not going to write that out, but T is still our parameter. It's still, all this stuff still works. It's literally parametric. But wait a second. Vectors are also defined like this. A vector R, if I had this just random vector R, and I said, you know what, how do vectors look? Well, vectors look this way. Vectors look like this. They have, what comes first, x, y, or z?
X.
They have an x coordinate, they have an x component. In fact, like honestly, this x is literally the x coordinate of the point because vectors are always defined by the terminal points for position vectors, and then that little I. Do you remember talking about that? You'd have an x coordinate, and then I, and then you'd have, what's next?
Watch it.
A y coordinate with j, and you'd have a z coordinate with k. I want to refresh your memory on this one because we're almost done with the whole proof of what vector function, not even a real proof, just putting stuff together, but this is what vectors do. Position vectors are always defined by the terminal points. We start where? Where do we start with vectors? Where? Origin. And they terminate at whatever this says. Do you remember talking about that? It was 3, 2, 1. It'd be terminated at point 3, 2, 1. So literally, if we had this format, the ijk, the standard basis vector, we go, well, yeah, that makes sense. We have the x coordinate and I telling us how far we move along the x direction, along the x-axis. We have, vector addition. We can add vectors together, right? We have the y coordinate, j. How far do we move along the y? And then the z coordinate, k. How far do we move along the z? And we put those together, we get a vector, but these are literally the coordinates of the point where this vector terminates. Show of hands, feel okay with that one. But wait, there's more. If we look back at this, what if we don't have an actual number x? What if we have this function that gives us a number x depending on what t is? What if we don't have the number y, the coordinate y, we have a function that gives us the number y depending on what t is? What if we don't have the number z, we have a function that gives us what the z is depending on the value of t? Well, then we can take this parametric expression for it and plug it into this vector and get a vector function. That's literally what a vector function is. It's a parametric definition of your xy coordinates plugged into a vector. That's all it is. So if we put these ideas together, by the way, what is this vector? What variable is this vector function going to be based on? So this is going to be a function, vector function, but it's based on t because that's the only independent variable that we have. We go, okay, well, yeah, you know what? It's using an x coordinate, but we don't have an x coordinate the way we think. Like a number itself, we have something that's giving us the x coordinate. We have a function for x. We have a different function for y, and we have a different function for z, And that right there is called a vector function. I want you to think, see how it plays out. I hope that you're with me on this one. Is it true that I can plug in the value of t and get an x value, a y value, and a z value? And if I have I, j, k, then every single value of t gives me a specific vector. Show of hands if you guys see that. That's what a vector function is. But what's it do? Well, before we get there, I want you to be thinking about that. Before we get there, just always keep in mind that's x, that's y, and that's z. Before we get to what it is, there's only one other way we can kind of see this. Besides having the standard basis vectors, I, j, k, we can also have that vector bracket notation. You remember dealing with that? It's the same stuff. So what would come first? X would normally come first. So in this case, it's just a function. And then y, and then z. X, Y, Z. I'm not going to write all of this out, just a couple statements. Keep in mind that for this to work, you have to have the same domain for what you're plugging in here and here and here. You don't get to pick some t's for here and different set of t's for here. You have the common domain. It works just like parametric. Does that make sense to you? So if you can't plug in 0 for the y, you can't plug it in for anywhere. Also keep this in mind. When you're finding out a specific vector, you need to use the same value of t. So if I want to figure out what's the vector at time, let's call t time of 3 seconds, you'd have to plug in 3 in all 3 spots to get that specific vector. It's kind of common sense, but I want to make sure that that actually makes sense to you. Does that make sense? So the common domain has to be the same domain for all of these, let's call them sub-functions, your coordinate functions. It's got to be the same domain. Also, what value are you using for your x, you've got to use for your y and your z to get that specific vector. So, what's it give you? What's it going to do? Think about that. Man. What's that? It's a vector. It's a function that gives you vectors, all right? So it says, hey, plug in a whole bunch of values of t, you're going to get a whole bunch of vectors. Does that make sense to you? A whole bunch of vectors. All of those vectors, are you listening? Start at the origin, yeah, but they all have terminal points. And if we let this value of t go through its domain, it's going to give me a whole bunch of vectors that point somewhere, like that point, that point, that point. And those points, listen carefully, okay? Those points, it's like connect the dots here. The terminal points of our vectors are creating this little dot plot that gives us a curve in space. So what vector functions give you are curves, called space curves, because you're going through space. They're giving you space curves. So what's happening here basically is we let R of t be a vector from the origin to some terminal point on a curve. It's not a surface right now. That's not what's happening. We can't just say, hey, and make this the surface. That's not what this does. What vectors do is they have one point, and if I let that vector move, let's say, let that vector move, it can go longer, go shorter, and it can move through space, but it's creating this curve for us through space. The terminal points of these vectors created by the vector function create a curve called a space curve. Show of hands if you understand that concept. It's kind of a weird idea. We're not traveling along this way anymore. We're traveling by going, bop, bop, bop. We're pointing where we're traveling. I'm going to draw you a picture in a second. The only thing I'm going to write is the terminal points of these vectors will be on some curve through space for the entire domain of t. you guys write that down? Here's what all of this says in English. All right, it says, and if you only write it out, I'll write it out too. So, a vector function. Here's the whole statement. A vector function is a parametrically defined function where the terminal points of these vectors trace out a curve in 3D. That is all that is happening. So the terminal points of the vectors trace out a curve in 3D. Because we have a domain for the independent variable t for our parameter, because we have a domain that goes from smallest to largest, it also has to have an orientation. It's got to be traveling a certain direction through space. Does that make sense to you? So if I'm going, hey, t equals 1, t equals 2, but where time has passed, the variable t is moving along also in its own domain there, which means that the vector points somewhere and then later it points somewhere else. That always gives us an orientation of travel. Head nod if you're okay with that one. It really should make sense, right? It should make sense because vectors are basically defined by their terminal points. So do you want me to write that statement out, by the way? Would that be helpful for you? Yes, okay. So basically, the whole punchline to everything. Well, I'm tired of writing. You tired of writing? I'm going to stop there. All right, good. My shoulder hurts. Got to do more doublets. So, a vector function is parametrically defined. Yeah, the parameter's t. Hello, plug in t's. That's going to give you vectors. That's what's called a vector function. Those vectors point to points. Their terminal points are points. Those points trace out a curve. That's what's going on. The fact that t has a certain domain, like it starts somewhere, it goes somewhere, makes certain that our vector function has orientation. It also goes in a certain direction. That's the whole idea. The only other thing that we want to talk about is that this really shouldn't be a problem for us because every vector, like ever, let's say a certain vector, r of t sub 0. Let's say it's negative 3, 5, 2. Okay, stick with me here. Point, vector. Which one? Both. It's a vector, yes, but it has that terminal point. What's the terminal point of this vector? What point is it terminated at?
Negative 3, 5, 2.
So the terminal point here our vector is negative 3, 5, 2. Yeah, it starts at origin. It points to negative 3, 5, 2, wherever that is. But its terminal point, where it's stopping, is at negative 3, 5, 2. If I take all of these little vectors and I put them all on my graph from the origin to their terminating points, it's going to create a curve. What a curve is this connection of an infinitely many points, right? Let those vectors point to the points, and we end up tracing out a curve in 3D. I think I've overtalked it. I'm going to stop with that one. The only thing I want you to know is that every single vector itself gives another point on that curve. The picture looks something like this. So this is coming around, wrapping up over top of the z, coming around the y, and then going on. Do you guys see the picture I'm trying to draw for you? Here's how vector functions really work. It says if I wanted to define this with a vector function, what happens is that I start with just a few examples here. What's happening is that a vector is pointing to these points. Let's call this r sub of t1. I know if you can't read that, that's okay. What's going on, I'm not even going to write this anymore. My first vector points, or a vector points to some point on my curve. And I start going, well, what's the next one? Let's say it's all of these things. And what's going on is that I'm pointing to terminal points on this curve. And that's what my vector function actually does. It says, hey, where am I at this point, at this time? I'm at this point. What about this time? I'm at this point. What about this time? I'm at that point. And I'm pointing to my curve instead of traveling along it. It's kind of a weird idea, but I'm pointing at where I'm at in space. That's the plan here. So if you guys feel okay with the plan. So this is the picture of vector functions, really. Pointing where the points are on the curve. It allows me to travel it, but not going through the curve, but standing at the origin, saying here, 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 here. That's the idea. Now, what's nice about them after all that talk is they're not actually that hard to work with. You're going to end up probably liking vector functions. We'll talk about just one example of vector functions. We'll spend most of our time sketching them because they're a little weird to sketch. But here's our very first example. Exciting. That's what the EX stands for. It's not example, it's exciting. So that you're not as excited as you should be. This is cool. Okay, you know what? I know it looks brand new to you because it is brand new to you unless you've had this class before. Can you see that this is a vector function? Can you see it? How can you tell it's a vector function? I could say vector and look inside the vector. There's t's in there, right? You go, oh yeah, functions. Vector given by functions, a vector function, that's it. Or if I would have put t's with like i's, j's, and k's, well, that would also be a vector function. There's a couple ways you can write it. Here's what I want you to understand. When we have this, yes, the x-coordinates and y-coordinates are going to be here, but they're given by functions of t. You're not going to see a whole lot of x's, y's, and z's. You're going to see a whole lot of the parameter. So what I want to do right now is threefold. I want to find the expressions for x, y, and z, because it's going to be very important in a minute. I want to find the common domain for the parameter t. And I want to find just one vector given by a point. So let's start with this one. Let's find x, y, and z. Can y'all tell me, what is the function that is giving us the x-coordinates here, or the x-component of the vector? What is that? Perfect. Hard? No, it's just the first one. It's just like every vector works, man. The x is given by square root of t. What's the y given by? And what's the z-component or the z-coordinate of our terminal point? What's that given by? Should fans feel okay with that so far? Let's start talking about the domain. Well, you know what? I'm going to erase this and move because I want to write the domain underneath each one. Hang on. If I asked you to, could you tell me the domain of t for, by the way, x, y, and z? Those don't have domains. You're not plugging anything in for x, y, and z. Those have ranges, if anything, what we can get out of x, y, and z. They don't even have domains. Our domain is always based on the only independent variable that we have, which is t. So let's see if we can figure it out. Can you tell me what t has to be, just for the x-coordinate? Everybody, come on, what's t got to be? Yeah, it's probably, we can do that. Probably easier to do it this way though. So t's got to be greater than or equal to 0. Yes, no? We know we can't have negatives in there. 0 is fine though. How about here? Could you tell me this? Could you tell me that one? What's the domain for the y coordinate or y component? What can't t be? Sure. Why not? Yeah, but anything else is fine for that one component. How about the z? What about, oh, do you remember? What can I plug in for t, for ln of t? Do you remember?
0 to 1.
Can I plug in 0?
No.
Can I plug in negatives?
No.
Do you remember what the graph looks like? No.
It's like a
Looks like that, pretty much like that. So anything positive I can plug in, but not 0, because as I go 0 from the right, I get negative infinity. So this says t has to be strictly greater than 0. Here's how I do all of these domain problems. I write out what, and this is what you should do too, write out the x, write out the y, write out the z. Find the natural domain, the stuff that actually works for x, for y, and for z, and take the most restrictive one. Take whatever is restricting you for the common domain. So you go, hey, you know what? I can be greater than or equal to 0 here. That's fantastic. But this one says I've got to be strictly greater than 0. That knocks this one off the board. This one doesn't even matter anymore. You go, oh, don't even care. Because that one's more restrictive. Does that make sense? And then we go, but wait a second, I also can't be equal to 1. So when we write our domain, we have to take all of that stuff into account. We say, what's the smallest value I can have?
2.
0, but not there, not bracket, parentheses. You remember talking about that? So I can start almost at 0. Where do I go? What's the next point that I have to consider here? I can almost get to 1. Can I include 1? No, that's what that means. But then anything after 1 is fine. So when we write out these domains for our parameter, for our independent variable, we go, okay, well, write out what you can't do, write out what you can do. I can be greater than or equal to 0, but this one says I gotta be greater than 0 strictly. So I know that the smallest value is 0 with parentheses. I know I can't have 1, so I exclude the value of 1, but everything else is good. Should fans feel okay with that one? That's how you do this common domain. Now the last one. Could you figure out 2 specific vectors? What happens at t equals 2 and t equals 4? The only reason why I want you to do this is so that you believe me that we actually get vectors out of these things. So if we want to find the vector at t equals 2, what number are we plugging in?
2.
Where are we plugging it into?
T.
Yeah, that's it. So at t equals 2, it says, hey, this is all based on t's, right? Plug in your t. So it's plug it in. So if I wanted to find the vector at t equals 2, go, okay, plug in 2. What's the square root of 2? I don't know. Leave it. Square root of 2. Can I plug in 2 here? Yes, of course. It's on my domain. You can plug in anything you want. As long, listen. There's only two little side notes, okay? You can plug in anything you want, provided you plug it into the same value of t for every single t, and provided that whatever t you're plugging in is in your domain. It has to be in the common domain. You can't plug in 1 here and here, even though it lets you, because you can't plug in 1 there. That's the nature of the common domain. You don't get to plug in anything that works for all of this stuff. You plug in anything that works for all this stuff, provided it's in your common domain. That's why we do that first. Does that make sense? So if I asked you to plug in 1, you couldn't do it, because like a third of your vectors are going to be undefined. You can't do that. So we'd have square root of 2. We'd have, looks like we got what? What's the next one?
Natural.
1 minus 1 is 1, or 1, okay. And then ln2, I don't even know what that is. Just leave it ln2. Now, what is that? What did we just find? It's literally just a vector. It's also it's giving us this. It's saying, hey, at the time t equals 2, I'm pointing at this. I'm going along this specific vector. I'm pointing at this point. That's my terminal point, and it's going to be on the curve that this thing defines. That's what's going on right now. Show of hands if you're okay with that one. All right. Find the 4 if you haven't done already. Easy, medium, hard. What do you think?
Easy.
So far, yeah. Looks like 4, 1/3, ln 4. Did you guys get the same thing I got?
Yep.
Oh, no. Hopefully you didn't. Yeah, whatever you say, Leonard. I'm not even listening anymore. I have to sleep, whatever. It's late. Tired. We haven't even gone 35 minutes yet. Good. So if you feel okay with the idea of vector functions. So if you want like a 20-second recap, here they are. Vector functions is a vector, vectors that are given by equations for x, y, and z independently, that when you put those components together, it gives you a vector. Points to a point on a curve. That's what's going on. We take all the vectors together, it gives us all the points on the curve together, it's just pointing at them. That's what's happening. In order to plug in points, though, you have to be defined for all three of those components at the same time. It's got to be defined. That's basically it. Now, we're going to move on a little bit. We're going to talk about how to sketch them, because you know what these things look like. So we're going to move on to sketching these vector functions. I'll give you a piece of advice before we keep going. Vector functions we're not going to deal with a whole lot of them, but they can have only two components. If they do, it's called a parametric equation. Graph them on a plane. Okay, don't worry about 3D because it's not 3D if you only have two components. It's going to be on a plane. Does that make sense to you? So I'll write a little blurb about that, but we're going to be sketching. I'm going to give you the general rundown. Some of this is not going to make sense yet because we have not done an example yet. But I'm going to give you the general rundown about how you sketch pretty much every vector function like ever, provided it's on a normal type of surface. So here's our general idea. Number one, oh my gosh. Wake up. Oh, good. Okay. Now you'll get number one. Number one, am I really that boring? It kind of...
No, we just pretend like we're not used to it really well.
Right, thanks for pretending. You do a great job, I can't even tell at all. Number one, OMG. Is that better for you people? Like toads. OMG, you're my like BFF. On the Twitter sphere, hash brown tag, LOL. Just throwing stuff on the line. I don't even know. Face space, my book, I don't care. Listen, number one, write down what X and what Y and what Z are. Independently, do not try to do it in your head. Literally write them down. Identify X, identify Y, and identify Z. Do that first. Number one, right off the bat, do it every time. Number two, use one for 2D. For 2D, it's you use both, but for 3D, for these actual curves, identify one or two components to make up a curve or a surface. Trust me, it's going to be vague right now because we're not doing an example, but this is what we are going to be doing. So number two, use one or more components to find a curve or surface. In order to do this, we're going to have to get rid of T. Okay, here's the deal. If you only have two components like X and Y or Y and Z or X and Z, if you only have two components, the curve that you find will be a curve. So it be a surface, just a curve, and it's going to be on a plane. So for two components, sketch it on a plane. for three components, you're going to be sketching that curve. Please listen. I don't want you to get lost here. Listen. Vector functions, they are curves. They are not surfaces. They are curves. So this, I've lost people before on this. Like, what do you mean you're talking about surfaces now? Yeah, but there's a caveat to this, okay? These are all curves. They're pointing to points, man. It's good. You're going to create a curve. That's what's going to happen. But what happens here if we use this model? These curves are going to be sketched on the surface of some of these surfaces. They're going to be like a cylinder. If it's a cylinder, it's going to be traveling along the cylinder. If it's a cone, it's going to be traveling along the cone. If it's a hyperbolic paraboloid, it's going to be traveling along the hyperbolic paraboloid, the saddle thing. That's what's happening here. So the idea is identify X, Y, and Z. Yeah. Use one or more of those to give yourself one of those surfaces that you know about. Paraboloid, cylinders. And then the curve that we have for these three components, the curve is going to be laying on top of that surface. So these things are not surfaces, but they can travel along surfaces. That's the difference here. I don't know if you understand the concept here. So what are they? Are these vector function surfaces or curves? Curves. But they can be traveling along surfaces. So for three components, the curve, the vector function, will be on a surface. And lastly, the last thing that we do, well, man, you never do it this way. You never just plug in values of t, get a whole bunch of points, and start plotting them. It ain't going to work out so hot for you, okay? But once we understand that we're 2D or 3D, once we understand that we're on a plane or on a surface, then at the very end, when we get a good idea what the surface is, then we start using values of t to get at least 2 points, because what those 2 points are going to give you, keep in mind, these things all have orientation, correct? So we're going to be able to travel along that surface with a given path. Go, oh, we're going this way, or we're going this way. So we're going to use at least 2 values of t to find out our orientation and to figure out at least a little bit of how the curve looks. So use some values of t to find some points and the orientation. Just keep in mind, man, you got to find points that are, this is why we did this. You got to use points that are actually on the domain. You have, that's just seem obvious, everything's got to be defined. So from here, number 3, use values of t to find points and orientation. Tell you what, we're going to do 2 examples and we'll pause for a break. We'll come back. We don't have that many, honestly, just a couple. Then we'll talk about limits and continuity, 2 of the easier things that you'll ever do in this class. And then we'll be done with our section. It's a quick section. So let's start with just some 2D ones. I know they're parametric, well, one 2D one, then a 3D one. They're just parametric, but I want to show you exactly how to work with them. So here's our first example. Okay, hey, first idea. Can you tell me that that is a vector function? Is that just readily apparent to you that that thing is a vector function at this point?
Yes.
It says, hey, vector given by a variable. That's a vector function. That's what that thing is. What is the one variable that we have up here?
T.
But it's also given us some components. That t should give us x, y, maybe z. So right now, number 1, I want you to write it explicitly. Don't do it in your head. Trust me. It's going to be a lot easier if you write this out. Trust me. Trust the Leonard. Has the Leonard ever steered you wrong? Only a couple times, but that's okay. Trust him on this one, all right? Write this stuff out because it's going to be a lot easier for you to do substitutions and make equations if you do. So what I want to do is I want to write out x and y and z. What is our x? What's it equal? Beautiful, you understand it. What's our y? What's our z? Oh, there's not one. How many dependent variables do you have?
2.
How many independent? So what that means is that we can put these together to get a curve out of this. If you have two components, sketch it on a plane. What plane? The XY plane. If you had X and Z, you'd sketch it on the Z. It'd look exactly the same, okay? It'd look exactly the same. It's just your axes would be different. Does that make sense to you? You had YZ, sketch on the YZ plane, but sketch it on a plane. That's what's going to happen here. So first we go, okay, hey, here's X, here's Y. I know I'm going to get a curve. I know it's going to be on a plane. It's two components, 2 dimensions. So start doing all that math that you know how to get rid of t. So use substitutions, use whatever you need. So for instance, here I go, okay, I know that x is the square root of t. I know y is 4 minus t. What if let's work here and try to do a substitution, or you can go this way, it doesn't really matter, but this would be a little bit nicer. Can I get this t so that I can make a substitution? What would I do over here?
Square.
Yeah, you do stuff like that. So x squared equals t. If x squared equals t, then y equals 4 minus x squared. Or if you like it better this way, I like it better that way, negative x squared plus 4. Here's the whole point. Identify x, y, and z. We did that. We only had x and y. Use one or more components. I used one component to get a curve or a surface. That's a curve, and I got rid of t. If you can do that, what that says is this is a curve. It's actually going to be on a plane because I only have those two I only have two components. So we're sketching on a plane. I'm going to sketch on the xy plane.
Why do we do substitution?
Because what we're going to try to do is get some sort of curve we understand out of this, all right? And so we go, well, you know what, I can't sketch this and this very well for myself, so let's do a substitution to get rid of that t. Just like parametric from Calc 2, when you graph every time you did parametric, if you think back, look at your notes, look at the videos, every time we did it, we basically got rid of the parameter. Like every single time. Why? Because we don't know what that is in our head. That's really hard to think about x and y independent of each other and then put it together. When we put them in one function, however, that makes a lot of sense because now we're rectangular. Watch carefully though. Can you graph that? This is, come on people, what is that? Opening downward, love it. And on the y-axis, that one. So this is, I'm going to give you a bit of advice with these two-dimensional stuff. When you're graphing the curve itself, graph it in a dotted line. Would you do that, please? Here's the reason why. When we graph this in a solid line, this is nature of parametric equations and nature of vector functions. This gives you way more than what we have in this graph, okay? So this is going to give you the curve that our curve is on. I know that's weird. It gives you the curve that our curve is on, okay? It gives you the pathway that our vectors are going to point to. Where the actual point to could be less than this. So I'm going to graph it like this. This is negative x squared plus 4. That's what that thing is. Listen, this can be, it's not necessarily super hard, but it can be confusing. Are you guys okay on identifying x, y, and z? Show of hands if you feel okay with that one. It's probably the easiest part. Are you understanding that we're going to use one or more components to basically get rid of t, to figure out some sort of rectangular sort of equation that we can graph? Head nod if you're okay with that one. If you have two components, graph it on a plane. If you have three, we're not there yet. We'll graph it in 3D. We're not there yet. And then when we sketch this curve that you find, please listen carefully to the verbiage, okay? This right here is just normal curve. The vector function will lay on top of this curve somewhere, or on top of the surface if we're in 3D. The vector this is not the vector function right now. This is the curve. You guys see what I'm talking about? It's the curve. The vector function is going to be on this. Yeah, but it doesn't have to be the whole thing. It's going to be part of it. Later on, we're going to have a surface. The vector function is not the surface. It's on the surface. Just like the vector function is not this curve. It's on the curve. I know that's a small point, but let's see what actually happens here. The last one is use values of t. Let's plug in -7. Should I do that? What should I plug in? Probably 0 to see where it starts. Because this is going to have an initial point. It has an orientation. We just start somewhere for a defined domain like that. So if I plug in t equals 0, listen though, where we're plugging points in, they have to be values of t. They're not values of x or not values of y. They're values of t. So we go back and we use this thing. Can you plug in 0 into my vector function? Of course you can. What is it?
4J.
I'm sorry, what?
4J.
4J. Oh, I thought you said 4t. I was like, no, guys, we're plugging in for t. 4J. Hey, 4J, tell you what, it's got a terminal point. What is it? 0. Did you notice how you got 0, 4 out of that? Actually, check your book. Is 0, 4 somewhere on this curve?
Yes.
If it is not, you have the wrong freaking curve. Okay? It has to be. 0, 4, this is the vector. Here it is. This is the vector, 0 or 4J. It starts at the origin, it goes up. That literally is 4J. The terminal point is 0, 4. That's literally the starting point. That's the initial point of this vector function right here. All we got to do is figure out which way it goes. So it's greater than 0. Is it going to go this way or this way? Plug in another point. Plug in anything you want as long as it's greater than 0. Plug in 1, plug in 2, I don't care which. Plug in 4. I'd probably plug in 4. Why? Because it's nice. And because I can show you the vector real nice. If I plug in 4, here's square root of 4 is 2i. 4 minus 4 is 0j. I have 2i. Can you tell me, is 2i, is the terminal point of 2i somewhere on this curve? Some of you guys aren't even arguing.
Yes.
Are you guys with me?
Yes.
Because 2i does this. Goes up here. Here's 2. 2i terminates at 2, 0. That's literally on my curve. And it tells you something. It says time is passing from 0 to 4. Here's 0, here's 4. So time is going like this. My vectors are doing, they're pointing at these points, going this way. What that tells me is that my curve starts here with my initial point. It's traveling this way along the curve I found, and it's going forever. And my vectors are doing this. It's pointing at all these points. My orientation, you don't have to show this. You don't have to show the little vector functions. I'm just showing you what it's actually doing. What you do have to show me is if it has an initial point, you got to show me that. If it's got a terminal point, you got to show me that. And you got to show me the orientation. Since we start here and later, we call it later time-wise, we hit this, I know the orientation is that. You did the same thing with parametric. It literally is parametric, but I know that a lot of teachers in Calc 2 just go through it very, very fast. I personally don't. But a lot of teachers do. They go, oh yeah, parametric, you get it later. Well, you're now getting it later. Here's my next question. This was part of the curve. Is it part of the vector function? No. The vector function lays on top of the curve or the surface that you find. That was the big deal. We don't even need that. That's the vector function. Show of hands if you're okay with that one. Okay, tell you what, do you guys want to take a break now or you want to do one more and take a break? I don't care, either way. One more? Okay, it'll be pretty quick. It's just going to be very fast. Leonard fast. It'll only be like 25 minutes, all right? I know, Leonard fast is slow. I'm sorry. I like to talk and hear my own voice. Did that come out? You know what? We're going to go a little bit quicker though, Leonard quicker, because we've done this already. So I want to outline the basics, but this one's will be faster, I promise. First question I got for you. Is that a vector function in your eyes? Yes, no. Vector function, yes, no.
Yes.
Absolutely, it's a vector function. If it's a vector function, you need to immediately identify what x, y, and possibly z are. Can you identify the x, y, and the z components right now? Go ahead and write down, would you? Left-siders, can you tell me what the x component is? Middle people, y component?
2 minus 8.
And right-side people, z?
2.
Did you make it through section 11.5?
Yeah.
What up, huh? What is that? You need to know right now. What is that? Come on, what is it? What is it? It's a line. Do you guys see the line? Do you guys remember lines? This is where lines came from. They are vector functions. They are parametrically defined vector functions. This is literally a line. Do you guys see the line? It's exciting. That's where it came from. I wasn't making it up. I did it twice now. I proved it twice. That's a line. That's it. It's just a vector function. But defined as a vector function, you should be able to tell me right now a point on. Oh, come on. You need to know it. Your test is coming up too. You need to tell me a point on that. Do you see the line? It's cool. This is a parametric. Oh, wait a minute. Do you remember the symmetric equations and the what was the other one besides symmetric equations? Parametric equation for a line. Do you remember that? You're not as excited as you should be. Parametric equation of a line. Can you tell me right now one point on this line? Give me a point on this line.
1, 2, 3.
1, 2, and that's a point on the line. How could I find it? Plug in t equals 0, and you could find that point. Plug in t equals 0. Seriously, here's 0, 0, 0. You'd have 1, 2, and 3. You'd have x, the y, and the z. That's the vector. I know that's the vector 1, 2, 3, but the terminal point of that vector is the point 1, 2, 3. And now if you're okay with that one so far. Could you give me, if you're like, well, wait a minute, what about all this other crap? Well, all this other crap says this. We're done. You already got the line. You know this thing is a line. Does that make sense to you? So we said, hey, can you identify x, y, and z? Yes. Here's x, here's y, here's z. Can you use one or more components to identify a curve or surface? Yes. Here's the surface. The curve. Here's the curve. It's literally a line. I know we have a line. Can you find, we know it's a line. Can you find some values of t to give the points and the orientation? If it's a line, the points are easy. The orientation says I'm traveling along the vector. The direction vector would be 1, -1, -2. You guys with me on that one? Okay. Can you give me another point on this line? So at t equals 0, notice that you have to know that though, right? That point happens at t equals 0. That's where we even got that idea, was 1, 2, 3, plug in t equals 0, you've got that point on that line. What's another good value? This one might be a little non-intuitive here, counterintuitive. What's another value that you would use?
-1.
I wouldn't use 1. We're plugging in for t, correct? I wouldn't use 1. I would use the value of -1, or I would use the value of 2, which is what I'm going to use, or I would use the value, I don't want to do that one. 3/2. Why?
They got intercepts.
Because I want things that are easy to plot, and things that are easy to plot are right around axes. I'd plug in something that makes this 0, or this 0, which is what I'm going to do, or this 0, which is what I'm not going to do. Plug in a value of t that makes one of your components coordinates 0. Use that. Use value of t to make at least one. One component equals 0. So I'm going to choose 2 because I don't want to go negative, because that's going to be, and it's also because it's, yeah, it doesn't really matter. You could use -1 or you could use 2, it's about the same. I'm going to use 2 here, I'm going to get 3, 0, that's what I want. That's why I chose the 2. And then, let's see. So I want to take it back, 20-second recap, make sure we're okay on this stuff. Did you see the vector function right from the start? You go, yep, vector function. Can you identify the x, y, and the z? Is that okay for you?
Yes.
Yes, no. Do you see that sometimes we get some nice stuff? Sometimes we don't even have to work for the curve. It's given to us. You got a line. That's just a line. Don't overthink it. It's literally just the parametric equation. No duh, it's got a t in there, of a line. I just pulled out no duh, it's like 6th grade. Welcome to 6th grade. Well, if we know it's a line, all you need to graph a line is how many points?
2.
You need 2 points for a line. To graph it on a graph, you need 2 points, because the vector, that's really hard to use, right? We could tell the direction vector. 1 point is given to us, but you need to know it's at t equals 0. The other point, you have to find that point. Plug in a value of t that's going to give you a component equal to 0. I chose 2. We get 3, 0, -1. And now if you're okay with that so far. And then we graph it. And would I graph this in 2D or 3D? What do you think? 3 components? 3D, it's a line through space. Now, of course, that means that you know how to graph or plot those points. If you remember how to do this, even if you don't, here it is again, because we didn't spend a whole lot of time doing it. If I wanted to plot the point 1, 2, 3, that's 1 on the x-axis, 2 on the y-axis, 3 on the z. Here's how to do it. Remember do you remember redrawing the x-axis and the y-axis and the z? Remember doing that with your curve sketching how I showed you in class? If you do that, if you redraw the y, but right from your x-intercept, if you redraw the x, but right from the y-intercept, you see how these things are parallel to the x? And it's just redrawing this. It's just redrawing your x and your y, but at the appropriate coordinates. Head now if you're okay with that one. Here's your x, here's your y. It's at y equals 2, yes, y equals 2, and x equals 1, yes. And where they intersect, right there, that is the impression or projection of this point on the xy plane. Like looking down from a bird's eye view, that's what it look like it's shooting through, okay? We just need to translate this 3 units up. There's 2 ways to do it. Probably the easiest way is this way. Just watch carefully. I can't do it a whole bunch of times, okay? It's this way. Wherever that projection is, take that, redraw something parallel to that from the height of that point. And then, just like we drew the parallel to the x, just like we drew the parallel to the y, we're also going to draw the parallel to the z, but you're going to do it from your projection. Erase a little bit. That is where the point 1, 2, 3 is. I know it's tricky until you get it, but the idea is a lot of parallel. Do the parallel of the y, where your x coordinate is. Parallel your x where your y coordinate is. Draw that line, draw something parallel, and then where the parallel to your z is, and where that intersects your diagonal line that we drew, that's where your point's at. I know it's hard to actually do, but did it make sense on how to find that? Took a little bit more time there doing that. I know we did it the first time we did 3D, but I did it fast. Now, why do we make one of these zeros? Because this is a whole lot easier now. Because when your x or your y or your z coordinate is 0, you're actually on a plane. So when I do my next point, my 3, 0, 1, everybody real quick, what's the x coordinate of 3, 0, 1? What's the x? 3. So I come out here. I know I'm at that x coordinate, head nod. What's your y coordinate?
0.
Ah, that means that from here, I don't go out or I don't go back. All I can do now is go up or down. How far do I go up or down?
1.
That's easier. You don't have to go sideways now. You go, okay, I'm going down 1. Which means that I'm going to draw parallel to my z. I'm going to draw parallel to my x, because all I'm dealing with is x and z right now. Correct me if I'm wrong, but my y is 0, right? So x and z is the only two things I want to draw parallels of. And where those guys intersect, that's my other point. You might want to watch that a couple times to see how I don't have time to do this all day long, okay? But this is how it works. We went out 1 over 2 up 3. That's 1 point on this line. Hey, we had it a long time ago. I'm showing you how to do it. Plug in something, makes one of these 0 because it's way easier. This is 3, 3, 0. I didn't move. Down 1. That's the other point. How many points do you need to make a line?
2.
So now we go, hey, this line in purple is simply going to go through these 2 points. It's hard to visualize that because that line is going through 3D, but that's what's happening. This is coming out of the board and going down. That's what that's doing. That's the first line we've ever graphed in 3D because it takes vector functions to actually think about it, to actually do it. Now, the orientation. Does this, think hard about it, does this have an initial point like this one did? Does that have an initial point? What's the domain of T? It goes forever, because it's a line, right? It goes forever. So it doesn't start anywhere, it doesn't stop anywhere, but it definitely has a direction. That's why we choose some good points and we put them in order. So we plugged in 0, yeah, that's this point. We plugged in 2. Is 2 happening before or after 0? So I'm traveling from here to here, not the other way around. So my orientation, I'm going to erase that so I'm not confused. My orientation is going from this point downward. So we're traveling in that direction. It certainly has a direction to it. Have I made this make sense to you? Can you understand the idea?
Yes.
Okay, we're going to practice a couple more complicated ones that are actually on surfaces when we come back. Okay, so back at it. Some real live vector functions. Stuff that's not just lines. Stuff that's not just 2D. Stuff that's real, like 3D. I'm going to show you exactly how to do that right now. So the stuff I've given you, now it's going to be a lot less vague. Those instructions are on the board. A lot less vague right now. If you read through those, or you have memorized, firstly, oh man, it's obviously a vector function. What's the first thing you always do with vector functions, like ever? What do you do? Let's identify x, y, and z. Go ahead and do that now. This is not the hard part, right? This is not the hard part is the surface, and then sketching on the surface. That's the hard part. So what is your x, everybody, please?
T.
Y?
T squared.
Z?
T cubed.
You guys are so geniuses. Love it. Okay, that's fantastic. And then we have a parameter t, and it's going from 0, positive, 0 to infinity, so that we keep that in the back of our head, that we are going to start somewhere on this curve, which is going to be on a surface. Now, how many components do we have? That is not a trick question. How many components do we have? We got 3. It's going to be in 3D. This is not going to be on a plane. It's going to be on a surface. What's the next instruction that I gave you? It was identify and then what?
Plug in plot.
I know, I wrote it down. Come on. It was number 1, identify X, Y, and Z. We have done that. Number 2, it said use one or more components to make up a curve or a surface. We're going to do that now. You can't graph this right now. Does anybody know what that looks like? The answer is no. I guarantee you don't know what it looks like. I don't even know what it looks like. All right? We're going to have to identify the surface that this is going to be sketched on top of. How we do that? Listen, use a couple components that are easier to work with. The idea here is t cubed, I don't know, but I see x equals t, and that's a direct substitution into either of these guys. Does that make sense? I'm going to do the easier one. I'm going to make this as easy as possible to try to figure out a surface. So right now what I know is that because I've identified x, y, and z, our vector function, our curve, is going to be on a surface, not on a plane, on a surface. Right now the idea is find the surface. And now if you're okay on that one, find the surface. How we do it, I'm going to use these two. Make it as easy as possible. I'll give you some notes on that in a second. If x equals t and y equals t squared, y equals x squared. And now if you're okay with that one. Are you sure you're okay with that? Okay, now. Before you answer, you got to think about it. We are in 3D right now, right? We're in 3D right now, right?
Yes.
What is that? In 3D, what is that? It's, how many variables do you have?
2.
It's a cylinder along the z-axis with a trace of... What's this look like on the xy plane? A parabola. This is a parabola projected along the z-axis. That's all it is. Is this making sense to you?
Yes.
We've literally done this before. That's why I said if you've done 11.6, if you know how to graph especially cylinders, this is easier. If you look at it and go, I don't know, this is impossible. You need to know, okay, there's 2 variables. I am in 3D though, because I have 3 components. That means that's a cylinder along the missing variable z with a trace of a parabola on the xy plane. That's what it is. Write it down. At least that much. It's a cylinder along z. Why? Because we're in 3D, and there's only 2 variables. So that means a cylinder. It's along the z-axis because there is no z variable right now. It's not even there. And it's a trace on the xy plane. A parabola right there. So right now, what I'm going to do is I'm going to trace out. By the way, we are sketching here. Okay, we are not being exact. We just need to know that this is a parabola on the xy plane. And it's projected along the z-axis. And it looks about like that. Can you guys see the cylinder that I've tried to create there for you guys? Head nod if you can see that. So this is a cylinder of that parabolic shape that's just traveling along the z. Now here's the whole big kicker. Firstly, if you do this differently, there are some other surfaces that you could get. So a little side note here. You can do this by substituting here. Obviously the surface is going to be different. It's going to look completely different. So how do you know what to do? Use the surfaces that you are familiar with. So I'm familiar with cylinders. I'm going to try to make cylinders as often as I can, and cylinders that are really easy to sketch as often as I can. So even though there's more surfaces possible, and you can do it differently, all it takes is one. You just need one surface. Am I making sense to you?
Yeah.
So a side note here is sometimes more than one surface is possible. You just need one surface. Any surface will work, but stick to ones that you know, stick to ones that are easy to visualize. More than one surface is possible, stick to ones you're familiar with. Cylinders. Cylinders are easy. Graph those sort of things. Other little side note. What two components did you use? First, right off the bat, what two components did you use to give yourself this surface? Which one did you not use? That is the one that will give you your curve. The component you don't use will give you the curve on that surface. Or I'll say it this way, because the next example, two examples from now is a little weird. The component you don't use first. I'm going to pause right there. There's a little bit more to that I'm going to say in just a second, but I want to make sure you're absolutely certain of what is going on. Firstly, look up here at the board. Do you understand how to get this surface? Do you understand that it is put it together, it is a cylinder along the z-axis with the shape of a parabola on the xy plane, just traveling right along. Do you understand that? Is this the vector function? Is this the curve that I'm looking at? No. The unused component is going to give you the curve. That curve is going to be on this cylinder. It's going to be right on the surface of that cylinder. That's what's going on. So the unused component gives the curve on the surface that you just made. In this case, it's a cylinder. On the cylinder's surface. It's a pretty cool idea of what we're doing. It's kind of neat. If you need it even more explicit, this gives the cylinder or the surface this is going to give you the curve. How? Well, let's think back to those directions that I gave you. Did we identify X, Y, and Z? Did we use one or more components to give ourselves the surface? The last thing says, if you want to read that again, the last thing says, find some points. Find some points on this thing. And if we know that this curve is going to be on the surface, if we find 2 points, we can estimate, we can sketch it. We're just sketching here. We can sketch what that curve is. So what's the first value of t that you're going to plug in?
0.
Yeah, 0, absolutely. Why? Because that's what your domain says. Start at 0, that's my initial point. Okay, now, listen, where are you going to plug it in? Are you going to plug it in here, or at the very beginning? That's what you're going to plug it into. That's the vector function. That's going to give you your terminal points. It's going to give you your points on your curve. So let's plug in t equals 0. And we'll do only one more. Okay, you know what? I know it's a tricky one, but plug in t equals 0, you tell me the point. What is that? Hopefully you're plugging in 0. Okay. 0. So the vector is the 0 vector. It's 0, 0, 0. The terminal point, now, so I'm cheating here, okay? I'm going to just write down terminal points. All I care about is a point right now. The terminal point is 0, 0, 0. So even though this is technically a vector, I'm talking about the terminal point of said vector. Head nod if you're okay on that one. Where's my vector function start? And that's literally where it starts. So right now in my purple pen, I know my curve starts right there. I know for sure. Now, the reason why we draw our surface is because it makes it a lot easier to plot points and a lot easier to estimate what that curve is going to look like. So let's plug in another value. You can plug in 1, but it's not very interesting. It doesn't give you a lot of shape to this. Does that make sense? I'd plug in something like 2. I won't plug in anything bigger because it's going to get big really, really fast. But I'd plug in 2. And when I plug in t equals 2, the vector is 2, 4, 8. The vector 2, 4, 8 has a terminal point at the point 2, 4, 8. Head and off you with me on this one. Listen, 2, 4, 8 has got to be somewhere on the surface. Just like 0, 0, 0 is somewhere on that surface. You guys get it? Just like the curve had to be on the initial curve, the vector function had to be on the curve, the vector function has to be on the surface. That point's got to be there. So we're going to estimate. Here's 2, 4, let's make it. Now I did that for convenience, okay? So that I know this point is 2, 4, 8. Why? Because I did it ahead of time, all right? But 2, 4, 8. Do you see how the point 2, 4, 8 is going to be on this cylinder right up here? It's on this cylinder. It's not inside of it, it's not out, it's on this cylinder. Head note if you're okay with that one. And if it didn't work out like that, if you didn't make your, I just kind of made it a scale. So 1, 2, 3, 4, 5, I made sure that was 8. Therefore, this curve does this. It starts here, for sure. After 2 seconds, it's going through that point. It's traveling along the outside of the surface, and it's going to continue on. It doesn't stop here. But it's going to look something like this. And we use this to go, well, you know what? That t cubed is climbing faster and faster and faster, isn't it? So when I sketch this, I'm not going to draw a straight line. I'm going to draw something that is an exponential look to it. So it's going to climb faster and faster and faster, but it's climbing outside of this. So it's going to look something like that. I always do it better fast. About like that. And the orientation is that way. I want to know if that one makes sense to you. Show of hands if it does. You feel okay with that one? So we had initial point. Yeah, it's got to be on the surface. Find the surface first. Find an initial point if you can. At least find 2 points. Sketch along the surface, not inside of it. Generally not straight lines along that surface. Are you sure it makes sense? Let's try another one. We're going to go through this one about the same pace. So, hey, firstly, do we get a vector function? Is this vector function going to go forever, or are we going to have a terminal point? For sure. Why? Because it gives me a definite domain for that. Now, with every single vector function ever, you should be able to identify x, y, and z. I want you to do that right now. Go for it. X, y, and z. Did you get those as X, Y, Z? You know, with the easy one like the line, it was pretty easy to see it was a line. I don't know what that looks like unless I can find a surface to draw it on. I definitely don't know what that looks like unless it... Do you know what that looks like? Here's what X is doing, 2 cosine t. Here's what Y is doing, 4 sine t. Go, and then Z, t. I don't know what that does. I know that Z's climbing at a constant rate. That's okay, but what's it climbing around? What's it on? What's it look like? That's what all this stuff does. This is put together a surface. It's a surface. It's going to be on the surface. We got to do the same thing with that. I don't know why my voice did that. Sorry. It's a surface. I can get all squeaky like that, too. It's sweet. It's going to be on that surface. It probably should because my voice is the same harmonics as this fan. So when I try to lower the fan out of the video, it also lowers my voice. It's very annoying to try to edit that. It's nice to just talk like this. It's way higher. But then you would all walk out. So number 1, you identified X, Y, and Z. Yeah. Number 2, use at least 1, probably 2 components. Probably not all 3. Sometimes we have to, but probably not all 3 to try to make up some sort of surface. Now, it's counterintuitive. You're going to use these 2. Why? Because you think back to parametrics. And if you think back to parametrics, you know that x equals cosine and y equals sine. It's going to give you a circle or an ellipse. That is what it's going to give you. Why? Because cosine squared, sine squared, that whole cosine squared plus sine squared identity equals 1. We can substitute for that. So I go, this one, that doesn't do much for me. Especially if I go, hey, y equals 4 sine z. I can't even graph that. So I don't even know what that means. But these two, I know that if I solve for cosine and for sine, if ever you see sines and cosines to the first power, not squared, just to the first power equaling x and y, if you see that, you can use the Pythagorean identity. Solve for sine and cosine. I know you're familiar with that, but you gotta see to solve for cosine and sine to be able to use that. So I know if I solve for cosine and sine, I got it. That's x over 2, that's y over 4, respectively. But I also know that cosine squared plus sine squared, as long as you have the same parameter, that always equals 1. Which means that if that always equals 1, I can take my cosine and substitute x over 2 for it. I can take my sine and substitute y over 4 for it. Now I've done some math here, I actually squared it, but you see where the x squared over 4, y squared over 16 comes from. Show of hands if you do feel okay with that one. Yeah, put it together. Come on, think about this. This is in, let's think about it. How many components do you have?
Two.
Total components.
Three.
It's going to be 2D or 3D? 3 components, 3D, for sure. Well, we use 2 of them, yeah, but what is it? Think 3D. That's why we think first, is it 2D or 3D? Because this is going to change, right? It matters. What is this thing? What is that? Cylinder. It's a cylinder along what axis?
Yes.
And the shape of the, what is it?
Ellipse.
Ellipse is on what plane?
X, Y.
Yeah, that's exactly right. So, do you guys see that that's a cylinder? 2 variables, but 3D, right? 2 variables, it's a cylinder. Cylinder along Z, it's going to have a shape of an ellipse, a trace of ellipse on the XY plane. I want you to practice right now. I want you to practice drawing this ellipse on the XY plane. Try to draw that cylinder. Try it. Seriously, I'm going to give you a minute. 1 minute. Try to draw that cylinder. I'm going to draw it as you're doing it, but I want to make sure you know where this thing is. It's got to be on the XY plane. I need you to know your x-intercepts, your y-intercepts, what axis it's along. Try it. I got something like that. Did you get this ellipse on the XY plane? And then we know it's traveling along what axis, everybody? What one?
Yes.
Something like that. Did you get a picture, at least something like that? Now, here's the whole big shebang. Is this the vector function? No, this is the surface that we're going to draw the vector function on. That's pretty cool. The z, well, okay, well, I gave it away. Gosh darn it. What's the one component you haven't used yet? Or at least the one you didn't use first? Yeah. Z equals t is the curve that's going to be on that cylinder. So right now, this is why we do it this way. We do the cylinder so we don't got to worry about how that curve is taking shape. We know that that curve is going to travel along this cylinder for a certain period of time. Now, how we do it, man, just plug some points in. Plug in some points. What's one point that you would definitely plug in right now?
0.
Okay, everybody right now, where are you going to plug that point in? Where are you going to do it? The very, very original part. So right here, you're going to plug that in. It's going to give you a vector, but vectors always have terminal points, which is really nice. It's going to give you a point. Hey, true or false? True or false? That point is going to be at the origin, yes or no? Let me ask you a question, see if you're really paying attention. Some of you are, some of you are not. Can this curve possibly go through the origin?
No.
Does this cylinder pass through the origin?
Yeah.
Then the curve can't pass through the origin. The curve, if you're getting it, the curve has to be on this soda can. It's got to be on there. If you get off that soda can, you're wrong. Okay? If you find any point that is not somewhere on the cylinder, you have made a mistake. Fix your junk. Because your math is off, all right? I don't even care what. I cannot go through there. Because my soda can it doesn't go through there. It's on the edge of that soda can. That's what's going on. So if I plug in 0, I get 2, I get 0, and I get 0. So 2, 0, 0. Hey, now if you're with me on the 2, 0, 0. Can you please put the point 2, 0, 0 on this graph somewhere and see where it is? Can you do that? What's the x-coordinate? What's the y-coordinate?
0.
Z-coordinate? Here's 2, 0, 0. Oh my goodness. Is it on the soda can? Is it on the cylinder?
Yes.
Kind of squash soda can. But yeah, it's right on there. Oh wow. What's the next value that you'd plug in? Don't say 2. I'd probably plug in pi over 2. Because that's an important one where things do interesting things. I'd probably plug in pi over 2. Now the z's not going to be very nice, but the x and the y are going to be very nice. Let's plug in pi over 2 and see what happens. If I plug in pi over 2 here, cosine pi over 2 is 0. Sine of pi over 2 is 1. Pi over 2 is pi over 2. You guys okay with that one? Hey, question. Is that somewhere on your cylinder? The point 0, 0. Okay, here's 0 for x. 4, 1, 2, 3, oh my gosh. And then up pi over 2. How much is pi over 2? Well, half of 1.6, roughly. What's the next value that you might want to plug in? Pi would work. What pi is going to do cosine of pi, what is that one? Good, -2. 0. Pi. Are these values making sense to you? Let's see if that's on the cylinder. Here's -2. Y, I'm not moving. Z, I'm on the back side of that cylinder. You guys see what's happening? What's going to go on? And the last one I'd plug in, I'd probably just plug in 2 pi, just to see what happens. I know I'm missing 3 pi over 2, but I already see what's going on here. I know I'm starting here. I know I'm traveling along this outside of the soda can. I'm going to hit here. I'm going to hit back here somewhere. Roughly there. Roughly there. So I'm going to come up here, I'm going to hit here, I'm going to hit here, I'm going to travel around, and then at 2 pi, I've got 2, 0, 2 pi. 1, 2, 3, 4, 5, 6, half roughly. So I'm kind of missing my point over here, but do you see what this graph is going to do? I want to, this is a weird one for people to see. Do you see where the cylinder comes from? Do you know the curve is going to be on the edge of the cylinder? So if it is, this point, man, that point, that's on the cylinder. This point, that's on the cylinder. This point, that's on the back side of the cylinder. If I did 3 pi over 2, it'd be on the edge this side of the cylinder. If I do 2 pi, it's right above the 2. I have to draw my parallel lines, so remember that. I've got to do that. So it's right above there. It's on the lip of that cylinder. That's where that thing is. Does that make sense to you? So, okay, well, let's draw it. I missed it. Let's make a point bigger. It's going to go on the back side. It's going to come up here, and then it's going to swing up. So it's on the front, it's going on the back, and then it's coming back on the front where you can see it. Can you visualize that? I know it's hard to draw, like 3D. Can you give me the orientation?
Up far.
It's going that way, that way, that way. So this is traveling up the edge of a soda can at a constant rate. That's what's happening. To me, it's pretty amazing that we can even draw this. I think that's pretty cool. Do you understand how to draw it? It takes a surface. If you try to draw that from scratch with just points, you are not going to get the spiral of a soda can. You're not going to get it. You gotta do it in the order I'm telling you. Identify X, Y, and Z. Use a couple components. You know it's 3D. It's going to be typically a cylinder. If you're just using 2, it's going to be a cylinder. If you got to use all 3, it's going to be a surface. Identify a couple variables that you can make a cylinder out of. Hopefully a cylinder. It's way easier. The one you don't use gives you the curve on the outside of the cylinder. How you find it, just plug in values of t and verify they're on the surface that you just made. Show of hands if you feel okay with that. I want to change this just a couple notes on it. I want to change it just slightly 2 times. I'm going to change it 2 times. Number 1, what if I change this to not t, but what if the t were a 3? What if the t were a 3? I hope you're paying attention because I don't have time to do like 13 more examples, but these are important, okay? If the t were a 3, that would be a 3. This would be exactly the same exact cylinder. But then when I got down here, this would happen. All these values z equals 3, right? What's that value?
3.
What's this value?
3.
What's this value?
3.
I'm not going to ask you. I'd still be on the cylinder. But what would happen is that up here at it was so pretty. Here's what happens. If I restrict a component to, like, say z equals 3, then the height cannot change, which means that my points still here. 203? Yeah, but it's not 200. 043? Yeah, that's right here. What's happening is I have a tuna can, and it's on the lid of the tuna can. That's what's going on. So this would be this way, hit here, and hit back here somewhere. Right there. It hit over here somewhere and be back. So it would just float right around the lid of that tuna can. So when you get a constant component, don't let it throw you. You still have the same surface. It's just restricting the height. You're not moving up and down. You're literally just rim riding that tuna can. That's the idea. Should parents feel okay with that one? Okay. The last one I want to talk about before we get into limits and continuity, which is honestly really easy, is this one. Can I change this one, or you want me to do a different one? You don't mind? You don't care? I'm not going to draw a picture of it. We're just going to change it and see what happens, okay? Instead of these numbers here, what if we do that? I'd like you to see how this stuff changes. And the reason why I'm doing it here is because it's going to be very similar at first, because the first thing you're going to look at doing is going, okay, X, I know what X is. I know what Y is. I know what Z is. Let's try to do the same thing that we just did with these two. Okay, I want to see if you can make it that far. You guys can identify X, Y, and Z. Head nod, yes or no.
Yes.
And if you saw the sine and the cosine, go, oh, sine and cosine of the first power, I love that. That's going to be the Pythagorean identity, and you are literally still going to do that. So we solve for cosine t, yeah, it's x over t. Solve for sine t, it's y over t. The only difference between this example and the one we just did was we had numbers here, and now those are variable. Listen. If the numbers are variable, then instead of getting ellipse after ellipse after ellipse after ellipse, I hope you're listening, instead of getting that ellipse after ellipse after ellipse, what I'm getting is this ellipse, and then the denominator grows. That's a bigger ellipse. And the denominator grows. That's a bigger ellipse. And the denominator grows. Oh my gosh, now I'm getting a surface. Do you guys see it? What type of surface? I'll show you how to find out. We go, well, now wait a second. I know that I could do cosine squared and sine squared and get 1. That's fantastic. And I know this would be x squared over t squared and y squared over t squared equals 1. Verify that you can get that far. And this is where most people get stuck. And they go, what the heck, Leonard? Because now I still have my t's in there. And you said, get rid of t's. That's right. Get rid of the t's. How do you get rid of the t's? Use the one you haven't used first. That guy. That's the only way. Because I've already used x and y up, right? I used these two first, my x's and my y's. The component you didn't use, now you got to bring in your pinch hitter, okay? So if I use z to represent this t, we get that. You guys are okay on getting that? That doesn't look so good. No, it doesn't. It doesn't look good at all. So try to put it into one of the formats that you actually understand. For instance, if I multiply both sides by z squared, this should be getting exciting. If I put everything on one side, what? I mean, ¿qué? I'm learning Rosetta Stone. I think that means what in Spanish, doesn't it? You gotta go to Costa Rica, man. I gotta learn it. ¿Qué? Este es una... I don't even know how to say cone in Spanish. How do you say cone in Spanish? I mean, oh, what is this? It's a cone. Think about this. This says cylinder where you're expanding. What's a cylinder where you're expanding? Well, it's probably either a what do you call those darn things? Hyperboloid or a cone. The cone is getting bigger. The cylinder is getting bigger. That's what's happening. It's a cone. This is literally a cone. Since that is positive, it's an upper cone. It's an upper cone. Do you guys get it? It's not the lower cone, it's the upper cone. It's like a funnel. That's what's going on. How can you tell? It's right here. This is I hope that you remember your section 11.6, because this is a 3 squares, no constant, 1 minus cone along the z-axis, just like we talked about. Did that make sense? What would happen here? I'm not going to draw it. Okay, I'm drawing. What would happen here? Here's your cone. If you start plugging in values from 0 to 2 pi, what happens is that this guy does a lot what our original thing did. It starts at the origin and starts traveling along that cone. And it spirals up that cone. That's what's going on. Now, of course, you plug in some numbers and figure that out to get the spiral. But that's traveling along that cone. You still use that component that you didn't originally use to give you the trace on the surface. So everything works. Identify X, Y, and Z. Use 2 of them at first to try to get yourself a cylinder. If you can't get a cylinder, use the other one to give yourself a surface. One that you know, like a cone. Then you reuse that one to travel along that surface. Is this explained well enough for y'all? Let's tell you what, let's go ahead, let's take our break. I want to talk to you for a second before y'all do, after I pause this, and then we'll come back and do limits continuity. All right, welcome back. Hey, since we're talking about functions, we get to talk about limits. Yay? I can tell by your happy smiling faces that that's a big yay. Well, here's the nice part about it. Limits aren't the best because there's a lot that can go wrong with them, like indeterminate forms, and you got to use L'Hopital's rule, and you have to understand what the pieces of the function actually look like. You got to know what they look like. But the good news about them is that there's nothing tricky that we're not trying to trick you here with limits. The idea of a limit is if you have the limit of a vector function, it's literally saying the limit of each component of the vector function gives you a limit of the vector function. So what that means is if you can find the limit of f of t, the x component, and g of t, the y component, and h of t, the z component, that will give you the limit of a vector function. Now I want to say a couple things about this. You can see it's incomplete. Firstly, it should probably go without saying, but I'm going to say it anyway. You have to go to this. You have to approach the same number for all 3 components. So if your limit of the vector function is approaching a, you got to let all these approach a. Furthermore, if you look at it, it says the limit of a vector function is, what do those brackets mean? What are you getting out of this? You're getting a vector. That should actually make sense. What this thing says is, hey, what vector is the vector function approaching as we're getting close to this value of t? Let's say, what vector are we getting close to? We're getting close to this vector. If you also think about it, the terminal points of this vector function, the terminal points are all on the curve, right? So from the right side and from the left side, we're doing the same thing. It's just we're not traveling along the curve right now. We're saying, hey, what vector are these 2 guys coming together at? That's what's going on here. So even though we're dealing with a vector function, it's just asking what vector does this vector function approach as t approaches a? And we're approaching this vector. It's just a vector. Head nod if you're okay with that one so far. Now, even though you can do these independently and just put them down, typically what I like to do is do the limit of each individual one because you're going to do different things for each component of this. For instance, if I want to, and I'm going to write the answer right here. If I want to find the limit of this, verify it's a vector function for sure. It's got vector notation. It's got some t's in there. T's approaching a number. And if you were in my Calc 1 or Calc 2 class, you know the very first thing you do with limits every single time is plug the number in, man. That's the first thing you do because dealing with continuity, if it's continuous, the limit has to exist. And it has to be the function of that, or value of the limit has to be the value of the function. So if we have something that's continuous, plug the number in. Works every time. The only place it doesn't work is when we're not continuous, and then you have some other tricks, things that you do. So I would find the limit of this. And this. And this, find the limit of each individual component, mash them together, and you got yourself a vector. So let's see, is there anything tricky about this one? Can we just plug in 2 and be okay?
Yes.
How much did we get? Beautiful. Can we just plug in 2 and be okay?
No.
No, in this case you go, well, but you can do other things. You can say, if I get 0 over 0, I know for a fact that that is a removable discontinuity, otherwise known as a hole, which means I can factor it and simplify out the problem. Boom, boom. Can you plug in 2 now?
Yes.
And how much do you get?
One.
Tell me something else you could have done with that problem since you get 0 over 0. You could have L'Hopital's rule. Would it work? Absolutely. You're going to get 2t over 1. Hey, plug in 2. You get 2 times 2 is 4. Do I care? No, I don't care at all. Factoring for me was easier here. I really don't care. I'm not here to teach you limits right now. I'm here to teach you that vector functions still have them, and you perform them the exact same way you always would. Plug in the number. If you can't, do other stuff. L'Hopital's is on the table. We're still dealing with curves, okay? All the factoring is on the table. How about this one? Am I going to have to do anything fancy with that one? Even though you got a fraction, there's no issue here. There's no discontinuity. You can't even get 0 here, so plug the number in. We get 2/5. So the only thing I care about here is that you're able to do limits of each piece individually, and then put them back together. The limit of the x component, y component, and z component create a vector. So you need to put it in vector format. That means that you have this with vector notation, or you have this. Either one of those is fine, and I don't care which. So what this says is, hey, what vector is this getting close to as my time, as my t is approaching 2? It's getting really close to this vector. That's what's happening. What vector at time equals 2? What vector at time equals 2? There isn't one. Why? Because it's not even defined. I can't even plug in 2 for that vector. So this would be considered like the whole part of vector functions. We don't have that actual vector. What it's getting close to, you remember that? How you can come from both sides to a limit, even though the point's not there, the limit still exists? That's what's going on here. Head nod if you're okay with that one. The next one, same exact thing. We still have a limit. It's obviously a vector function. We have x, y, and z. Let's write out the limit of each of those components individually. Why don't you go ahead and do that right now? Limit of cosine t, limit of tangent t over t, limit of t ln t as t approaches 0 from the, you remember what that means, from the right. For you guys, from the right. Can anybody tell me out there, what's the limit of cosine t as t approaches 0 from the right? If you don't remember that with continuous functions, right and left don't even matter. Just plug the number in. Doesn't even matter. So since cosine t is continuous everywhere, it has no asymptotes, no nothing, just plug in 0. What's the limit of cosine t as t approaches 0?
1.
So from the right, it must also equal 1. You guys okay with that one? There's also a couple ideas like, hey, what's the limit of tangent t over t when t approaches 0 from the right? And you go, wait a minute, that's 0 over 0. L'Hopital's. Because L'Hopital's gives you stuff like secant squared, and you go, okay, well, could you do it? Why not? You can do things like that. You can rely on some identities. I've proved this in Calc 1. But you can see this is equal to 1. Why? Because the limit of sine t over t as t approaches 0 is 1, and it's based on that. You can do things like this. I'm cheating because I'm not going to write the limit, which I would kill you guys for, but You can do things like that and switch them. You go, hey, limit of sine t over t is 1. Cosine t, that's also 1. So 1 times 1, this limit is 1. So if you have that one, you could do L'Hopital. You can do a lot of stuff with this. All said and done, though, did you guys catch that? But a limit. That limit, that's an identity. It's proved by the squeeze theorem in Calculus 1. And it's on the video if you want to go see it. But that is 1. So limit of sine t over t as t approaches 0 is 1. This is, as t approaches 0, 1 over 1. 1 times 1 is 1. Now this one, that's a nasty piece of fun right there. Because you go, that's, crap. Yeah. How much is that when t approaches 0? 0. How much is this as t approaches 0 from the right? The only reason why we have from the right here. What is it? Negative infinity. Remember the ln. So 0 times infinity, that's called an indeterminate form. And when we do things like that, you have to change one of these to a denominator. We go, okay, this is ln t over 1 over t. Then it becomes from 0 times infinity, it becomes infinity over infinity. That's the indeterminate form. Look it up from Calc 2. That's section 6.7, I believe. So look that up for indeterminate forms. After you change to an indeterminate form, so from an indeterminate form, you should get 0 over 0 or like this, infinity over infinity. Anytime you have 0 over 0 or infinity over infinity and you can't factor, and you don't have identities, that's when you have to use L'Hopital's rule. So you use L'Hopital's rule here. L'Hopital's rule is derivative of the numerator over derivative of the denominator. And then simplify. And plug it in. And plug it in. So don't forget L'Hopital's rule. Don't forget that we can do things with indeterminate forms. You just can't begging. Praying, begging? Both, okay? Look, please don't do things like this. I'm begging you. Hey, 0 times infinity is 0. Yay! It causes me to drink at night. Please don't do that, because sometimes it does, and sometimes it doesn't, and you won't know when. Please don't do things like 0 over 0 equals 0. Or sometimes it does. Sometimes it equals 1. You have to go through the motions you actually have to do to learn it. Show of hands feel okay with these ones. If you are struggling with this, you can see them outside of class. I'll explain indeterminate forms to you all day long, or you can watch Calc 2 indeterminate forms. But that's what that one's going to be. All said and done, though, does it give you a specific vector? Yeah. Write down what that vector is. What is it? Simple answer for a hard problem. Hey, what vector is this vector function approaching as t is approaching 0 from the right? That vector, 1, 1, 0. That's the vector that's happening. Show of hands feel okay for real. If you don't remember things like this, tan inverse of t as t approaches negative infinity, this would be that. Here's tan inverse. Remember that function? Bottoms out at pi over 2. Don't forget things like that. This would be negative pi over 2. Stuff like this. Exponentials when you approach negative infinity. Exponentials look like this. They have horizontal asymptotes. So as we're approaching negative infinity, this guy is approaching 0. Just a little couple basics, but I didn't want to leave you hanging. I don't have time to go over more limits. I apologize for that, but we're not in here to learn limits again. We're in here to learn that limits are done really straightforwardly. You plug in the numbers if you can, each individual component. If not, you have L'Hopital's, you got factoring, you got L'Hopital's, you got indeterminate forms. Use those to your advantage. Are there any questions at all before we continue? Could you write that in standard basis form? So when you see in the back of the book, you go, man, I'm not seeing 1, 1, 0. How could you write that vector another way? Yeah, so either way, that's fine. Now, last little thing in our section, kind of a nice little thing here. Continuity. It's pretty basic. Here's what we know. In order for a vector function to be continuous, each component has to be continuous. In order for something to be continuous, it has to be defined. This means you got to have a definite domain to it, right? So basically, finding out where a vector function is continuous is finding the common domain. Like 99% of the time, that's all we do. So with continuity, just look for the domain, and if it's in the domain, it's going to be continuous on that domain. So let's find out some continuity. We'll practice just 2 of them and be done with this section.
Is there anything new on Thursday? Ms. Money?
Yes.
Is there anything new on Thursday?
We'll talk about that later. So continuity. Honestly, it comes down to finding domain. To find the domain, we did it earlier. Firstly, vector function, yes, no?
Yes.
Is this vector function defined everywhere for any value of the parameter t? Is it defined anywhere? Where is it not defined? Okay, so we know stuff about continuity. We know that if we have somewhere we're not defined, then we don't have continuity at that value, which means we either have a hole or we have this asymptote sort of idea. That idea still works here. So what we look for is, okay, hey, let's look at our first component, x component, cosine t minus 1. Is cosine t defined everywhere?
Yes.
Simply anything. How about the over t? Is this whole piece defined everywhere?
No.
What problems do we have? Can't be. How about this one? How about the square root of t? Is that defined everywhere? What do we know about t in that case? What's it got to be?
Can't be negative.
Got to be greater than or equal to 0. From that piece, that's what we get. How about the denominator? What value of t from there can't you have?
Negative 1.
Are you guys getting the picture here? Up here, that value of t, can that t be anything? This one right here? Yeah, that's fine. How about that one? Can't mean that's redundant, but we write down all of these pieces and then we put them together. So from our first component, we go, yeah, t can't be 0. Obviously, it's on the denominator. I know that t's can't be negative, so it's greater than or equal to 0. I know t can't be negative 1/2 because denominators can't equal 0. I know that t's fine. That's the only good looking one up here. And then I got that t cannot be 0 because we can't have denominators that are 0. That's the idea. We're not talking about limits. We're talking about being defined. We're talking about continuity right now. And now if you're okay with that one. Now put it together. Let's look at the most restrictive pieces. This one says I can't equal negative 1/2, okay? But this one says I can't equal 0. That says the same thing. But that one says I got to be bigger than 0. Does this even matter? If I've got to be bigger than 0 anyway, that doesn't even matter. But then this comes in and says, but you can't be 0. Can you tell me where this function is defined and where it's continuous? Where is it continuous and defined? They have to all be defined at the same t. It's called the common domain. So I know it's defined and continuous on the interval t is strictly greater than 0. The negative 1/2 doesn't matter. It's not even in that most restrictive region of continuity. With me? Yes, no? What do you think?
Yes.
Okay. Let's do what? How about you try it? At least parts of it. You know, this is clearly a vector function. Is this vector function going to be defined everywhere? So therefore, is it going to be continuous everywhere? It's not defined in places, it can't be continuous places. So let's take a look at it. I want you to look at least the first component and the last component and write down some things about it. Left-siders, what's that tell you about this? What values of t can't we have for the first component?
2.
Can't be, I'll take the 2, but also, what else? Because you said equals 0, add the 4, take square root, plus or minus, or you factor it. The last one, what values of t can't we have for a cube root of t? Any? Can I have positives in here?
Yes.
Can I have negatives in there?
Yes.
Can I have zeros in there?
Yes.
All values. This is fine. So the cube root of t, you can put anything in there, which means it's continuous everywhere. There's no problem with the, think about the cube root of t. A cube root looks like this. Almost looks like the tan inverse. That's what it looks like. It's continuous everywhere. This one, that's going to have an asymptote at 2 and negative 2 because you can't factor that out. It's going to be asymptotic. Vertical asymptote's there. I don't know if you're with me on that one. This one's weird. That one's weird. So you go sine inverse of t. Goodness. How high does sine get and how low does sine inverse works this way. It takes sine, which goes negative pi over 2 to pi over 2 and negative 1 to 1. It says, okay, sine inverse flips those. So if I can get out negative 1 to 1 from sine, I'm getting my inverses confused. If I can get out negative 1 to 1 for my sine, that's what I get to plug in for my sine inverse. So the only place this is even defined is if I get negative 1 to 1. Does that make sense to you? Sine inverse, the inverse of sine says you can plug in anything to sine, yes? Plug in anything to sine. But what can you get out of sine? You can only get out things from negative 1 to 1, right? So the inverse says you can only plug in things from negative 1 to 1. That's all you can get out. Or sorry, all you can plug into sine inverse because it's all you can get out of sine. Now, what's relevant here? Is this relevant? That's not the most restrictive thing in the world, all right? It says you plug in anything. Is this relevant?
Yeah.
You better believe it. I can only plug in numbers from negative 1 to 1 here. That's it. That's all it's defined for. Is this relevant?
No.
Not with this one. So this says, I'm not even defined outside of this range. This doesn't matter. This doesn't matter because I can't even plug in numbers outside of negative 1 to 1. So we are continuous on that interval. One thing I do want to say it this way though. Be sure that you can use interval notation appropriately. You need to know when to use brackets and when to use parentheses. The equals, you have brackets, not equals, no brackets, you use parentheses. Have I made this make sense for you, at least limits and continuity? That's the rundown. It's actually not the hardest thing in the world. Any comments, questions at all about this stuff before we take a little pause? Not break, pause. You good?